So before I go on, you have another question?
Yeah, how would you call a pushback?
How would I call?
Or how would you use
Okay.
it?
How would I call pushback? It's a member function of every vector. So you just write the vector dot pushback, and then the value that you want this next element to have, whatever.
Could you allocate that to a space in particular?
You're.
Oh,
I
to
mean,
the next one.
the next one.
Okay.
Yeah. It's the.
Yeah,
If you would ask for the vector size right here, then the element, this element here will have the index position of that size, so that you will have. Yeah.
Yeah.
Okay, you got that. Good. Okay, so our next chapter, wait, before I go on into this, are there any questions concerning the vectors, the strings, the C strings? Yes?
If the vector is of type double and I push back, like, let's say a 1 without the point something, would it go to 1.0?
Yeah, yeah. Remember, there's an automatic conversion.
No matter what I do?
There's an there is an automatic conversion, not no matter what you do, but there's an automatic conversion from an integer to a double. So, I mean, you were able to have a double variable and assign an integer to it, and before the integer was assigned, it was converted to its double equivalent, and then it was assigned to the double variable. Same thing here. This pushback creates a new variable that will be part of the vector, and then if you assign an integer or try to pass an integer to it, well, that since the double is required, that integer is first converted to a double, and then it proceeds with the assignment. Other questions or doubts? Okay, so our next topic is going to be pointers and dynamic arrays. Who of you has ever heard of pointers before? Nope, never encountered pointers, only one. Okay. Some people will tell you that pointers are a difficult topic. Hmm? No, not really.
I guess not now.
They're not really that complicated. I mean, there's a lot of things that you can do with
Reading into
pointers.
them this year, I don't find them as difficult as last year.
Good.
But last year sucked.
Well, I hope it wasn't my fault.
No, I just didn't understand. I was lost since like chapter 7.
Okay, so yeah, so what are pointers? It will turn out when we discuss pointers that you've already worked with pointers without knowing that you were working with pointers. I mean, even here on the slides, not necessarily on your homework, where you're always a little ahead. The array parameter variables. Remember? Array parameter variables? An array parameter variable is a pointer without any restriction. Yeah, that's the same thing. Okay, so first off, some motivation. What do we want to do with pointers? Pointers give us a way of referring to one variable at one time and to refer to a different variable at another time. So, in a sense, they have something in common with the references, but a reference that you form for example, if you call a function and you pass in some variable, and that is a call by reference parameter, then what happens? Well, as the call happens, the alias of the parameter name to the variable is being established, and then while the function runs, that cannot change. You can pass a different variable in the next time you call the function, and then you would have the same parameter name be an alias to a different variable of the calling function. But for the execution of that function, the reference is fixed. It cannot be changed. You cannot just say in the middle of a function, I now want this reference to be a reference to that variable instead of to this one. With pointers, you can do that. So with pointers, you have a way to refer to variables, and you can make the pointer change to which variable it refers throughout the execution of your program. So at one point during the execution of your program, the pointer might be referring to the variable A, and at another time it might be referring to the variable B. Okay, so, and we're also going to talk about dynamic arrays. Dynamic arrays are built using pointers, so we first need to talk about the pointers. And the dynamic arrays, they form like an in-between between the static arrays and the vectors. Remember I told you the arrays that we've talked about up to now, they have their size fixed when you write the program. So that is very static. Whenever you run the program, and you didn't recompile it, well, the array is going to have the same size. The vectors, on the other hand, don't have any fixed size at all whatsoever. Even while you're running the program and the program has already gone through several iterations of a loop, whatever, you still don't have to fix the size of a vector because it can always grow. And now dynamic arrays come in somewhere in between. You're not specifying the size when you write the program. You are allowing the program to obtain that size while it is run. So at runtime, either through input by the user or through some data that you read from a configuration file, whatever, yeah, you obtain a size that the array has to have, and then you dynamically, or your program dynamically creates an array of that size. So dynamic arrays strike a middle ground between the arrays that we talked about and between the vectors. What are the advantages, you might ask? What are the advantages of a dynamic array over a vector, for example? Well, they're a slight bit more efficient. I would say that in most cases, that doesn't justify using them. So in most cases, I would suggest that you do use vectors. But there are some cases where you need the last bit of speed, and then maybe you would have to try that out. You'd have to actually time your program running on some sample data. You would try out, is it faster if I implement this storage here of this data using a dynamic array, or is it faster if I implement it using vectors? Okay, so pointers. The slides that we're going to talk about they have some flaws, in my opinion. I mean, not saying that they're really wrong, but I like to point out or emphasize certain things that I think the slides are a bit vague about. One thing is right here at the beginning. Just like a variable is not exactly the same as the value stored in it, in the same way, strictly speaking, we distinguish between a pointer and the value, which is going to be an address that is stored in that pointer. Now, of course, when as I said earlier, or some other lectures, when you talk about a program, you often use maybe the terms variable and the value stored in the variable interchangeably. We say we multiply the variable with a value, but what we really mean is we multiply the value stored in that variable with another value. So, what did I say? So there is a distinction between a variable and the value, but when we colloquially speak about a program, we sometimes don't really point out that distinction. We to make it more convenient to talk about it, we use them interchangeably. Well, in the same thing is true with pointers. We often talk about pointers when we really mean the address stored in the pointer, which is the value that the pointer holds. Or we talk about an address when really we should be saying that this is done to the pointer that holds the address. Okay, so salut. When we have a situation, some situation of the program where we have a variable here, then from the start of this course, I have always told you that each and every one of those variables will have an address in memory where it is stored. So let's say this is at address 123. Well, a pointer is a variable, so it occupies some space in memory, and whatever. Now let's call it differently. So it occupies some space in memory, so it itself has an address in memory. Let's say 456. But the value, here we have maybe the integer 15. The value that is stored in a pointer is the address of a variable. So for example, we might have this situation, remember. We might have this pointer pnum here point to the variable number of pods. So,
so the value of a pointer is the address of a variable?
Exactly. The value of a pointer is the address of a variable. And the pointer is a variable itself. It's a special kind of variable. A variable that can store not integers or doubles or whatever connections to files, but instead addresses of other variables. And on the slide 6 it says an address used to tell where a variable is stored in memory is a pointer. Again, according to what I explained to you just a few minutes ago, maybe two, the address is the address and the pointer is the pointer. The pointer is the variable that stores the address. So the address, an address used to tell where a variable is stored in memory is an address, and such addresses are stored in pointers. And pointers point, we say a pointer points to a variable by telling us which address it has, which address the variable has. Okay, so another way of looking at this is that we get this level of indirection. Here we have a variable, so by the variable name number of pods we can get to the variable in memory. But now we also have this level of indirection. We can go to this variable and look up the address of a variable and then go to that location and use the variable at that point. Yeah? So we have this level of indirection that we can use to refer to variables. Every pointer points to a variable of a specific type. So you can have a pointer to a double, a pointer to an int, a pointer to an output file stream. Or a pointer to a string, or a pointer to a vector of doubles. Every pointer always points to a variable of a specific type. And you cannot just interchange them. I mean, you cannot just use, you cannot, for example, use a pointer to int to point to a double variable. And in order to declare a pointer, you just use this asterisk. On slide 7, you see that?
Yeah.
You use the asterisk in front of the variable name, and that indicates that the variable of that name is not a variable of the type that is there at the beginning, in this case double, but instead the type of P in this case here is a pointer to a double. Also, it's important to understand that declaring a pointer does not do anything for the variable. It creates that pointer, but it doesn't create the double to point to. Yeah?
That's my question. Well, how would you do that?
Well, you just have to add another variable. So one way to do it would be like this. And now you would have a variable. And now you could say, well, we get to that in a moment, because we need one more operation. But I think it's just the next slide. Not quite. Yeah, not quite. Okay, this is how you could have a mixed declaration. So you can mix the declaration of pointers together with the declaration of regular variables of that type, non-pointer, and so yeah, as you can see on that slide, this asterisk is, so to speak, sticky to the name in front of which it appears. So the way to read this is int pointer p1, pointer p2, and int v1 and int v2. Yeah? So it's not that you put int pointer and then every name that occurs in that declaration is an integer pointer. You select this, whether it needs to be a pointer or not, individually for every name.
What are pointers good for? What would you use them for?
Well, we'll get to that. I have a few examples for that. We'll get to that.
It sounds so weird to you can use this one, like this address, instead of just using them.
Yeah. One thing that you can do with pointers is you can use a pointer to scan over an array, for example. You set the pointer to point to the first element of the array, and then you just increment the pointer, and so it will go over every element of the array. That's just, we'll get to more examples.
Oh, that sounds pretty cool.
So I told you how to declare a pointer, but I haven't told you yet how to obtain a value, namely an address, that you can store in a pointer. So that's the next thing. How do you obtain an address? One way of obtaining an address is by this. You can write this as on the slide. Yeah. How do I read this? How is this supposed to be read? This operation here is read address of. Yeah. So what we're doing is assign to P the address of V. So in order to create this situation over here, what we would have done is we would have written p underscore num is assigned the address of number of pods. Yeah. Yeah. Take the number of pods, take the address, take that address and store it as the value of p num. Yeah, what? Still have to, one more thing to go. We know how to declare a pointer. We know how to obtain an address of another variable to store into a pointer. And the last question remaining, so to speak, before we actually can work with the pointers is, how do we get to the address that has its how do we get to the variable that has its address stored in a pointer? So if we have a pointer and the pointer holds an address, how do we get to the variable that has its address stored in that pointer? So if we look at p num, how do we get to this variable here? Because that's not the value of p num, right? If we just write p num, then the value of a variable is the value stored there, right? So in this case, it would be this address. But if we don't want to work with the address, but instead we want to work with a variable at that address, how do we do that? And that is called dereferencing. The operation is called dereferencing. It just means following this link, in a sense, yeah? It's like, in a way, this is similar to when you have an HTML document that you're looking at and you're clicking on a link and you're going there, yeah? In a way, it's similar to that. So, yeah. The syntax for that is, again, the asterisk. So if I write, for example, this, cout insert dereference, that's read now as the dereference of p num. So if I say cout insert the dereference of p num, what happens is that p num is a variable. So its value is being looked up. So this, in a first step, this translates to the address 123. Now there's this dereference operator. The dereference says go to that address and use the variable at that point. Use that variable at that point for what? Well, for inserting its value into cout. Okay, so again, like we had with the arrays, where the square bracket operation was used in two different senses. In the declaration, it had a different meaning than when it was used outside of the declaration. Remember? The declared size was within square brackets, or outside of the declaration, it was the index position that we wanted to access. In a similar way, the asterisk here is used with two different senses, two different meanings. If I use it in the declaration, I'm saying this is a pointer. If I'm using it outside of the declaration, I am using the dereference operation. I'm applying the dereference operation to whatever address is stored in the pointer. Okay, so now we have the three fundamental operations. You know how to declare a pointer, you know how to obtain an address to store in the pointer, and you know how to get to the variable pointed to by a pointer. So on the next slide we have another example that illustrates how these things work together, and it's always helpful to keep a memory diagram on the side to follow what goes on in memory. So here we have a variable v1, a pointer variable p1, and we have, and that's it for the time being. Okay, so let's say this is at address 2000, and we haven't done anything yet, we start executing those instructions. V1 has a 0 assigned to it. Then P1 is assigned the address of V1. So address of V1 gives us this. Assign that to P1. We have the address stored in the pointer. So now we have the situation that this pointer P1 points to the variable V1. Now, when we say the reference of P1 becomes 42. So, P1 is this address, address 2000. Dereference that means go to that address and use the variable at that address. Use it for what? Use it for assigning 42 to it. So what we're doing is we're assigning 42 to this variable here. Yeah? Through the pointer, we have changed this variable. This is just on the side. This is called an alias now. It's called aliasing. We now have, through the dereference, we now have an alias for the variable v1. And obviously, if we now do a cout v1, well, that's obvious. We get 42. If we do a cout insert the dereference of p1, well, take the address, go to that address, use the variable at that address to output it to cout. We're also going to get the 42. Okay, if we have two pointer variables and both pointers point to variables of the same type, so for the sake of simplicity, let's just say they're both pointers to integers, then we can assign the address that is stored in the one pointer as the value, as the address stored in the other. And so we can write something like this. P2 is assigned P1. We can write that, for example. Or, yeah, that's exactly what's there inside. What happens if we do that? Well, no, wait. I'm going to do that in a moment. Yeah, namely on this slide. For beginners, it might be a little maybe a little bit confusing to keep these two things here separated, namely the assignment of the value of one pointer to be the value of another pointer compared to the assignment of the value pointed to by one pointer to be the value pointed to by another pointer. There's a big difference. And by now you might see why from the start of the semester I've always drawn you these memory diagrams, because they're extremely helpful in thinking about what goes on with code like this. So in our example now we have two integer variables, let's just say a v1 and a v, and we have two pointers, a p1 and a p3. And where these pointers p1 and p3 are located in memory, that doesn't really matter. So I'm just going to leave that empty for now. But these are interesting. Let's say this is 1500 and this is 2000. And let's say we have the situation that p1 points to v1 and p3 points to v, meaning we have the 1500 here and we have the 2000 here. So now what happens if I do a P1 is assigned the value of P3? Well, both pointers are variables. If a pointer, if a variable occurs on the right-hand side of an assignment in an expression, then its value is just fetched from memory. What is the value of P3? Well, that is this address 2000. And it is assigned to be the value of P1 because P1 occurs on the right-hand side of the assignment. So what we're doing here is we're just overwriting the address stored in the pointer P1 so that both pointers now point to the same variable. And if we assume that we have a 10 here and a 20 here, then V1 has not changed, V has not changed, but the dereference of P1 has changed because previously the dereference of P1 took us to V1, and so therefore we would have obtained the value 10 from that variable. Now the dereference of P1 takes us to this variable, V, and we have, if we would use the value, we would get 20. So the dereference of P1 has changed because P1 has changed and now points to a different variable. Now the alternative is, or the other thing on the slide is, I'm just going to go back to the original state. Now if we do a dereference of P3 is assigned to be the dereference of P1. What happens? Well, first we need to obtain the dereference of P3. Go to that address, use the variable at that address. So use that variable on the right-hand side, on the left-hand side of the assignment. Use it to assign it to the dereference of P1. The dereference of P1, use that address, go to that location memory, and use that variable here. Use that variable to be overwritten by the value of that variable. So now we're changing this value here to 20. Observe the pointers still point to their separate variables, but the value of the variable has changed. Yeah? So that's a big difference. And it should go without saying that to really wrap your mind around this, you should play around with this a bit. Yeah, there's nothing that beats practice. Okay, now we have a better diagram than that. Okay. So there is another way of obtaining an address of a variable, and that's with the new operator. And the new operator does not only get you the address of another variable, it first creates a new variable. It creates at runtime a new variable, a variable of which you as a programmer, well, you didn't really know how many of those variables you were going to need, maybe. And so you deferred the creation or the declaration of these variables until runtime, when your program runs. So your program can create at runtime new variables using this new operation, and the result of the new operation is the address where in memory the variable was created. So if I have this situation in memory and my program executes the line there on the slide, P1 is assigned a new int. What happens is that somewhere in memory a new variable is created. That variable doesn't have a name. It doesn't have a name because we didn't create it at compile time when we wrote the program, so it doesn't have a name. But of course it has a location in memory where it is stored, and that's the result that we get back from the new operation. So in this case, when we ran, if we would run this code, we would get this situation here like this. Yeah. So new int is another way to get an address of a variable, even if that variable didn't exist at compile time, or well, I should say even, but it's the difference of those variables is that they are created at runtime as opposed to variables that you created when you wrote the program. That's why we call these dynamic variables, because they're created at runtime. Yes?
The line on the slide P1 equals new int, is that assuming that there was already another line upwards that declared the P1 as
Of course, yes. Yes. Okay, I think that's it for today, or is it? Yeah, it is.